Good afternoon, everyone. Well, it's evening. I don't know. Good evening, everyone. Today, Franklin will be going over how to apply PCA to pairs trading and like other pairs trading stuff. It's good. I like the notebook ahead of time, and it's pretty cool. So hopefully, you guys will enjoy the workshop today. And so, if you want to start, okay.
Yeah, I'll go ahead and start sharing my screen. Let's see. Oh, hold on. Of course, technical difficulties. 1 second. Hey, I need to leave the meeting in order to allow Zoom to share my screen, so I'll be right back. Hey, sorry about that. Let me share my screen. Okay, can you guys see my screen?
Yes, it's working.
Okay, great. So let me drop the link to my GitHub in the chat for this notebook, as well as the .py file that the notebook is running. Okay, so this is an application, so this notebook is an application of this paper that I will also drop in the chat. So the idea is that pairs trading is a strategy used by a lot of different financial institutions and hedge funds, where you look for pairs of securities. It doesn't necessarily have to be stocks. I mean, it could be any financial instrument. I mean, cryptocurrencies, treasury notes, stocks, for example. So you find two securities that move together. So whether it would be Pepsi and Coke, or Goldman Sachs and Citi, Amazon and Google, you're trying to find two securities whose prices generally go up and down together. And so the idea is that if Google and Amazon are moving together and you start to see that Amazon is outperforming Google, the thesis or the idea behind pairs trading is that the differences in the spread between those two securities will mean revert, and then you short the winner and buy the loser so that you can profit in up markets, down markets, sideways markets, etc. And so there's a lot of academic literature behind this, and these two authors use a machine learning approach to find pairs. So as the number of financial instruments are increased, if you have 600 securities, choose two. So that's 180,000 different pairs of securities to trade for, that are potential pairs for pairs trading. But odds are, out of 180,000 pairs, there's going to be some spurious correlations and things that are just kind of data mined. And so these two authors use principal component analysis and then optics clustering to reduce the number of potential pairs to find securities for pairs trading. So following their notebook, or following their paper, it's really broken up into 3 parts. So the first is dimensionality reduction via PCA, and then unsupervised clustering via optics, which we'll go over a little bit. And then the authors, in order to further reduce the chances of spurious correlations, or they introduce 4 other just practical criteria for the potential pairs to meet. So starting off, just state 0, we're going to get some data. So the data for this data set is 600 publicly traded securities And then I got the daily close for just 600 sampled securities, and I pulled it from Quandl. I mean, you can use Yahoo Finance. You can really use any data set that you want. That was just the data that I had on hand. So the full data set is ranging from 2010 to 2020, January 2010 to October 2020, and we use the first 9 years of that data for our training set. So here we can see read in a pandas data frame of the securities. It's a date time index, and so I've divided up into the training and the test sets. So this is just indexing to grab the years from 2010 to 2018, and then the test set is grabbing 2019 to 2020. So the first step, so I created a class that we're going to go over after this. The class is called optics pairs, and so then to initialize it, you initialize it with this training set of data, which is right here. So this is just the first 5 rows of the training set. Here you just have the daily close prices for 600 different securities. So when you initialize using the price data, this class will automatically give you the daily returns for each security. So here you can see on January 5th, this security had a negative 5% return and 0.47% return, etc. So it goes ahead and calculates the returns, the daily returns for all the securities. So once the daily returns are found, the reduced PCA function for this class automatically scales and then computes the correlation matrix for the price series. In addition, it computes the daily returns, scales them, computes the correlation matrix, and then runs the correlation matrix through principal component analysis. This defaults into giving the first 10 components. You can use any number of components, but the authors suggest using less than 15 because after that you start to run into some cursive dimensionality issues. So below, we're plotting the loadings for each security on the first principal components. So as you can see here, there seems to be a clear pattern within the first component. It looks like almost all of the securities have a positive loading. Some of them have a pretty strong, some of them pretty low. But in general, almost every single one of the 600 securities has at least the same direction loading on this first principal component. And you'll see this quite frequently within financial time series, especially within PCA analysis for financial time series data. And in general, this first component is thought to be the quote-unquote market component, which, if you're familiar with the idea of the beta of a security, this is essentially that's essentially the same interpretation as this first principal component. Given the fact that each of these securities comes from the U.S. stock market, we expect there to be some sort of common component that will affect all of them together. So this is unsurprising. And then, as you can see, you have loadings on the first, second, third, fourth, and fifth component, and the interpretation starts to muddy a little bit after that first component. However, so once we've implemented PCA, we've reduced the size of our problem drastically. So in our original data set, the dimensions are roughly 2,000 by 600, and then after PCA, we have reduced it to just a 10 by 600 problem. And so this, it really reduces the amount of data that we're looking at, and and even though there's a large reduction, we're still able to explain with these 10 components roughly almost all of the variance within the data set. So as we can see here, I've plotted the cumulative explained variance of these first 10 components. And if you look right here, the first component 0, which is this market component, this component explains roughly 84% of the variance within the securities. So moving on to unsupervised learning, state 2, what we're doing is we're applying the optics clustering algorithm not to the returns themselves, but to the loadings on each of the components. So you can think of it like if so instead of having where you can think of the X, Y, and Z axis into 10 dimensions that we reduced it to, but the loadings on those first components. And so the authors opt to use this optics algorithm rather than a k-means clustering algorithm, which is pretty common in different machine learning applications. The reason why they do this, and they if you read the paper, it'll explain it a little bit more, is that it's able to you don't necessarily need to include each data point or each security into a cluster. So for example, there might be some securities that really don't fit any sort of cluster. However, algorithms such as the k-means algorithm will force every security to be labeled. So this is another way that the authors are reducing the chances that you're finding spurious correlations by letting these algorithms decide which outliers don't need to be considered for certain pairs. So what we do is we apply this optics algorithm, which is in the sklearn, Python package, and we find 429 potential pairs. So what we've done is, I'll move down here and visualize. So this is just a scatter plot of the loadings of every security. So each of these dots is one security. The loadings on the first and second component. So as we can see here, up in this upper left-hand corner, there seems to clearly be, roughly 10 or so securities that are acting in that have similar loadings on the first and second component. And so what this find pairs up here, what this find pairs function does is it says, okay, each of these 10 securities was labeled the same label under this optics algorithm. Now let's find each combination of securities within this. So it reduces the 600 choose 2 into a 10 choose 2 algorithm, or a 10 choose 2 problem for this set of securities. And it's hard to see because all of these dark points are considered outliers. So if you look closely though, you can see that there's a couple yellow points right here. So this yellow cluster would be another one. There's a green one down here. And it's a little bit easier to see if you graph it using 3 dimensions. So here's that same yellow cluster in 3 dimensions, and there's a green one there, and there's a lighter green one there. But basically what this algorithm does is it grabs 10 or so securities that are the same, and then says, okay, here are all the potential pairs within the same cluster using the loadings on the components. So we've already reduced our problem from roughly 180,000 pairs to test all the way down to 429. So we've already reduced the computation time needed to run this to find pairs drastically by orders of magnitude already. And so what the authors have done is have said, okay, we have 429 potential pairs, but let's go ahead and run these through a couple more tests just to ensure that we're going to get some quality mean reverting pairs for pairs trading. And so the authors have suggested 4 separate criteria in order to find high quality pairs for pairs trading. The first criteria is a statistically significant t-stat from the Granger test. And so the Granger test is a test for co-integration. And to break co-integration down into 1 or 2 sentences, It's a test to see if you can find a linear combination of two securities that are stationary. And then
Or maybe
this,
I could draw it out if you like me. Here, I can draw it out real quick.
yeah, sure, that'd be great.
I'll use my paint skills that I've developed.
Yeah, do that.
Yeah, I'm gonna override your screen sharing for a second. Okay, so say this is our data. That's one. You guys can see my screen, right?
Yeah, I can see it.
Oops. Let's get another data. Okay, so it might not be exactly, but it's like this maybe. You see that? They look pretty similar. They're not perfect, but if you take the difference, say we take the difference and plot it onto another graph, it probably look like this. Probably looks something like this. So you can see that this is a stationary series, and a stationary series means that like the constant mean over time, and the variance doesn't stay. It's usually stay, and the variance is relatively the same. Here, to best explain what stationary is, let's give a counterexample, something that's not stationary. Oops. This is not stationary because the mean, it goes up, right? If we like plot the mean here, like say, let's just look at here. The mean is there, right? But then let's look here. The mean is here. And you can see that the mean is constantly increasing. Hopefully that makes sense. And then let's, oops. And then here, what happens if we had this? And this is also not stationary because you can see that the variance is increasing over time. So this is also not stationary. So we want stationary stuff because stationary stuff is nice to work with. Like a lot of time series model, it's nice to work with. So yeah, so stationary moves. Oops. So co-integrated pairs, the difference, like we can create some linear combination, like, oops. So they tend to move together like this, right? So like just take when we like, we can take some like positive factor of this and like some negative factor of this to get like something that like is like just like this. Okay, and hopefully that makes sense. Okay, back to you.
Yeah, thank you. So let's, right, and then we'll see examples of that later in this code. And then the second test that the authors run is a security with a Hurst exponent less than 0.5. And so we'll go over this code later, but a Hurst exponent less than 0.5 indicates that a time series reverts to the mean, strongly reverts to the mean, rather than a time series that potentially diverges from the mean. The third criteria that the authors suggest is a half-life in between 1 day and 1 year, or 252 trading days. And this is so the half-life is the time that it takes a value to revert to half. And if it's less than 1 day, it means that the spread is going to be moving too quickly in order to capitalize, in order to trade on it, and because we're using daily data. And then longer than 1 year indicates that you'll need to wait too long in order to have the pair mean revert. And basically it's just that, you're not going to be, it's just trying to avoid having to wait too long in order to realize gains. And then the final criteria is that the spread must cross the mean 12 times per year. And so this is just another way for the authors to enforce that the pair has that there are enough tradable opportunities for the end user. So here we calculate the Granger t-statistics and the spreads, the normalized spreads, the Hurst exponent, the half-lives, and the average number of times that the pair crosses the mean. And we filter on these above criteria. And here we found 20 tradable pairs out of those 429 pairs. And so this is a data frame which shows you the pairs of securities to be traded, as well as the p-value of the t-statistic for co-integration, the Hurst exponent, half-life, and the average number of times that the pair that crosses the mean over 1 year. So as you can see, all of these have a p-value of less than 5%. So they're significant at the 5% level. They all have below 0.5 on their Hurst exponent, which means that they strongly mean revert. The half-life ranges from, it looks like 24 is the lowest to, let's see, 80 is what it's looking like the highest, or 82. So they have reasonable half-lives, and additionally, you're going to get an opportunity to trade on each of these at least once a month. Once a month. And so below we plot the raw price series of the two securities, as well as the normalized spread. So this is similar to the MS paint that that we were just shown, where we see these two securities. This is the pair number 7. So we have right here this pair right here. So we have two price series that seem to be moving along similar price paths. You know, we see sort of a slight decline here, a little bit longer decline here with a little bit of a rally, and then you can see they both jump at a similar time and then remain flat, and they have a steady down coming in into the end of 2018. And so here is the normalized spread of the two securities. So this is that linear combination that I was speaking about earlier, where you have the difference between two series and then some factor times the other price series. So as you can see here, it's got a mean of 0. So, you know, it seems to be roughly moving about this 0 blue line right here. And it appears that there's a constant variance. You know, you don't see wide ranges here and then small ranges here. It appears to be roughly stationary in terms of variance throughout the time series. So, and then the red lines just indicate one standard deviation move, because these are the z-scores. So this was the first plot, and then each of the next 19 are pretty similar, where although you see that they're not necessarily, like, because the scales are different. See, for example, this blue security has prices ranging from roughly 30 to about 70, and this orange one has roughly 10 to 28 roughly. So although you're seeing some white space in between here, that's okay, because we're using a multiple in order to calculate this spread. So the two prices don't necessarily have to be within the same absolute value, because you are creating a portfolio of the two securities. So each of these below, you'll see that they have a stationary spread throughout each of these. So just moving down, so this is all of the 20 pairs that we found, and you can go back and look at this later if you're interested. Oh, and then one note, so as you can see here, it's counting the number of times that it crosses 0. So it looks like this one crosses a couple times here, and then 2014 to 2016, you know, there's a lot of trading opportunities here, and then several trading opportunities in the back half of the testing set as well. So just moving down throughout these. And so then here's just a further application of these trading pairs. You know, you can make several rules. You can make, now that you have a stationary data set, you can make your own rules to trade on this. So for example, you could only open trades when it reaches a 1 or a -1 standard deviation, and then close trades when it reaches the opposite. You could do 2 and 2. Or now that you have a stationary data set, you can really make, you can just become creative with how you want to trade on this. And so here's just a further application of where Professor Tim Leung, who is actually the director of the CFRM program, he uses this Ornstein-Uhlenbeck model to find the optimal price that you should either enter or exit a pairs trade. And I will drop later in the chat. I'll drop a link to a link to this ML Lab, which is a free Python package that you can download online, run by Hudson and Thames, where they implement different machine learning models for financial machine learning. And so they've implemented Professor Leung's model, where they find the optimal entry and liquidation price for pairs of securities when you give them the data. And that's just what I'm doing here with these, looping through these first 5 tradable pairs. So we initialize their Python class. We train it, giving the training data of the 2 pairs that we use. And here I've just set daily frequency to daily, the discount rate, and transaction cost. These are just numbers that I input just for an example. And here we are, and then later we plot the optimal levels for entry and exit for each of the pairs. So given in Professor Leung's paper, we see that each of these first 5 pairs closely followed the model. The training data closely follow the Ornstein-Uhlenbeck model, which we can tell by comparable max log likelihoods. So as you can see, these 2 are extremely similar, as well as these almost to the 3rd decimal level. And here we find that this first pair, it actually reached the optimal liquidation level roughly 50 days into the testing set. So, if you held this pair's portfolio at day 0, roughly 50 days later, you would have liquidated the portfolio. And then the other ones, as you can see, this one is roughly remaining stagnant. This one is slowly moving upward, but hasn't quite reached its optimal liquidation level. As well, same with this one. This pair is slowly moving upward. However, it's got a long way to reach before the optimal liquidation level. And this one has never reached its optimal entry level. So you would never actually, over the 2 years of testing data, you would not have entered this portfolio pair. So this is just a little bit of summary. So here we use empirical data to reduce the search space and find roughly 20 pairs for a pairs trading strategy, and then use this current model, or use this Ornstein-Uhlenbeck model to find the optimal entry and liquidation prices for those 20 pairs that we found. If you guys have any questions on this, happy to answer. Or if you'd like, we still have some time, I can dive into some of the code behind this notebook if you would like. So it's really up to you guys.
Yeah, that was freaking awesome. That's super cool. Wait, how'd you find the paper? Like, I'm like checking SSRN. These days I'm like checking SSRN or ArcSiv. All the papers are garbage. How'd you find this paper? This paper seems pretty good.
So I found this paper on Hudson and Thames. I was just doing some research on the projects that they're working on, and this was on their this was just like one of the skill set challenges that they had available. So I believe I think I posted the paper in the chat. Did I not?
Okay. Yeah. SSR and ArcSiv, like 90% is just pure awful. Maybe I need to check out Huns and Thames. I'm gonna find the papers from here.
Is the paper inside the Python notebook?
Yeah. So I have a link to the actual book, but I can edit the notebook and drop the paper in there. Do you see the?
It's in the chat. I see it.
Yeah, it's in the chat right here. So this is the paper that it's 10 pages, pretty short. So this paper or this notebook really just covers the first portion of this paper. So this proposed pairs trading framework. So covers A, dimensionality reduction. So it's reducing via PCA, and then B, the unsupervised learning clustering, which is using this optics clustering technique. And so here's a good illustration. If you can see my page on page 3 of this paper. So you see these just this toy data set right here in this upper right hand corner. So if you're using an algorithm like k-means clustering, it might say, okay, here we have cluster A, here we have cluster B, and here we have cluster C, and it would try to force every single one of these data points into one of those 3 clusters. However, you really within A, there's 2 distinct subclusters within this upper left-hand corner of the box, and so this optics algorithm allows you to throw away some data points and find more refined and more detailed clusters, subclusters within a larger cluster. And then part C is that pair selection criteria, where it goes over the Granger test, the Hurst exponent, as well as the half-life and the number of times that it crosses the mean. And then the authors go on later to use some. They go on later to propose a trading model that you can use these spreads to forecast. And they have some crazy good results, but I haven't. I was just implementing the first portion of the pair selection process.
You got a charger? Your laptop's kind of running out of battery.
Yeah, no, I know. Unfortunately, I'm away from my desk, and so
okay.
no charger. But I think that we'll be able to make it. I think that we'll be able to make it.
Yeah, that seems to be good.
So if you want, I can, just run through this code is on my GitHub, but I can just run through what the functions are doing kind of under the hood, if that's something that you guys would like to look at.
Yeah, I think that was only like 35 minutes, so yeah, we can go over it, I guess. I don't know.
Okay. Yeah. So this was in the notebook, all of the functions were coming out of this class that I wrote, this optics pairs. Here's just a description of it. It's implementing those first three components of the paper. So the class, when you initialize it with a data frame. The data frame is going to be stock or financial security prices, one period prices, and So the prices is going to be equal to the data. You know, you grab the securities from the columns of the data frame, and then it goes ahead and automatically calculates the 1 period returns for the prices. So this is just using that percent change function from the pandas data frame. So then going on to reduce PCA. So this is this function. It takes in the returns that have been calculated and then reduces the dimensions equal to the number of components that you want. The authors suggest using less than 15 components. So I've just initialized it or set the default value to 10. PCA requires or is best if the data that has been input is scaled. So here I used a min-max scaler. I think that going forward, I want to change this to a standard scaler. So so making like each of the returns like a z-score function or a z-score instead of using this min-max scaler. And this min-max scaler is from sklearn and their pre-processing library. They've got a whole bunch of ways to pre-process data, including a bunch of different types of scalars. So here we run a couple checks just to make sure that you have in fact calculated the returns. And this little line right here throws up a warning to the user where you can use more than 15 dimensions for the PCA, but the authors recommend using less than 15. So this pipeline is a pretty cool feature of sklearn, where you can essentially take an input and then run it through all sorts of different calculations, all in one motion in order to output another item. So what this pipeline does is it takes in returns, and then first it normalizes them by the scalar that you have selected. By the scalar that you've selected, automatically calculates the correlation matrix of the scaled data, and then performs the PCA dimension reduction of that correlation matrix. And so here we fit and transform the returns. We grab the loadings on each of the components. This is just for later on. We grab the number of components that were used, and then here we grab the percent explained variance for each of the components. Does anybody have any questions so far? Oh, sorry, I see that there's one thing in the chat. Is everybody following me so far?
Yeah, makes sense.
So then here, this find pairs function, it's going to use the optics algorithm, which is in the sklearn library, to find clusters of similar securities in the PCA space. So what we first do is we initialize the optics algorithm from the sklearn library, and we fit the function using the loadings on each of the components that we found from the PCA. Here we get a data frame of all of the securities and the clusters that this optics algorithm has assigned. And so here, this code is just grabbing or is removing all of these securities whose label was -1. And so this -1 is just indicating that it's automatically generated from this optics algorithm, and -1 means that none of the securities that the securities labeled as -1 were not assigned a cluster. So it just treats them as noise or outliers, and it doesn't. While you might have a lot of securities that are labeled as -1, those securities should not be treated as if they are in the same cluster. So those are all those dark data points that I was pointing out in that 2D and 3D graph, where it looked like there's a ball of dark points all labeled together, but in reality, you should not include those in different clusters. So here, given that cluster's data frame, we're grouping by each of the cluster. So what we're saying is, give me all the securities that have been labeled 8, for example, and then give me every combination of securities that meet that, or that are in the same cluster. So you might have security A and B, and security A and C, and security B and C, for example. So give me every 2 security combination that has the same cluster label from this optics algorithm. And then here we're just cleaning this up to flatten the list of lists in order to get just a list of all the potential pairs. And then returning that pairs just as a series, just for use later on when we're filtering. Continuing down, we have this calculate Engel Granger and the norm spreads. So here we're calculating the p-value of the t-statistic from the Engel Granger co-integration test, and then once that is found, we're going to calculate the normalized beta adjusted spread of those potential pairs. So if you look in the paper, the authors recommend to essentially run each Engel Granger test twice, where the only difference is which security price series is the independent variable and which one's the dependent variable. And it wants you to grab the p-value of the one that has, they're going to be essentially the same, but this is just a further test to ensure that you're not that you're grabbing that you're not data snooping. So that's what we do here. So we have each of the pairs, and we're saying, give me the first security prices and the second security prices, and then we're going to run this co-integration test twice. We're going to calculate the t-stat and the p-value for each of those, and then if it's lower, we're going to append the lower one, and then set the that security as the independent for the linear regression as the x variable, and then the other security as the independent variable for the linear regression. So moving down, we calculate the linear regression of the 2 time series in order to find the spread of the 2, in order to create that stationary mean reverting black spread that we saw before. So we find the intercept and the beta given the linear regression of the 2 price series, and then we calculate the spread as the first security minus the constant times the beta, or minus the constant plus the beta times the price series of the second. So this gives us the spread of those securities, and then we just calculate the z-score of that spread in order to make the graph a little more readable. You don't necessarily have to do this step, but generally what you'll see in literature and what you'll see with pair trading strategies is a z-score of the mean reverting series. So here we convert, this is just converting the spreads from a list to a data frame, and returning the data frame so that the end user can access it, as well as returning the p-values for the EG tests. So here we're calculating the Hurst exponent of the normalized series. And so a little bit further down, I've got a helper function that actually calculates the Hurst. So we just take in the normalized spread and then calculate the Hurst for each of the spread time series and return the Hurst exponent. And then this function calculate half-lives, essentially the same as the Hurst, except you're calculating the half-life of the spread instead of the Hurst exponent. And so here we calculate the average number of times that the spread crosses the mean. So in this case, the mean is going to be 0. So we find the number of days, and then we find the number of years that are within the original price data frame, and then we calculate the number of times that each series crosses the mean value, and then just divide that by the number of years to then filter to make sure that you have more than at least 12 per year. And then from here we are this is just a function to filter all of the summary statistics that we've calculated before. So here we create a data frame of each of those series that we calculated above. So we create a data frame that'll have all of the pairs with each of the columns being a separate statistic. And then from there, we just filter each of the pairs. We filter each of the pairs given the user input criteria. So each pair must have a p-value of less than 0.5, a Hurst exponent less than 0.5, a max half-life of 1 year, a min half-life of 1 day, and then must cross the mean 12 times. And so then this function is just selecting the pairs that meet each of those criteria. So yeah, so it just meets each of those criteria, and then it'll spit out a data frame of the filtered pairs. And so then these are just some checks to say, like, if this filtered pairs is an empty data frame, it's going to say, hey, look, you didn't find any pairs. You might need to relax some of the criteria. So the criteria that you would want to relax, I mean, you wouldn't want to relax this Hurst exponent, for example, because if it's greater than 0.5, it means that it indicates that the series has the potential to diverge. So really, you would want to probably relax either the max p-value to maybe 0.10, or maybe extend this max half-life to a little bit over a year if you were going to be more patient, or maybe reduce this min average cross to say 5 or 10 or something instead of 12, in order to, while you might have a mean reverting series, you might have less trading opportunities. And then here, this is just plotting. These functions below are just some plotting functions to plot the pairs. I guess how familiar is the chat with matplotlib and some of the plotting or like visualizations of time series or of data in Python? Is this something that I need to review, or is that helpful? Let's see. Yeah, I can go over it. So here we're going to plot the pair price spread. So this function, I'll show you the output of that. So this function is going to be plotting. So this function is outputting these two graphs right here. So let's see if I do this. Why don't I do this? Yeah, so just so we can see this side by side. So we're going to plot the pair and price spread. So this required list is just making sure that we have all the data points that we need in order to generate these graphs. So with matplotlib, one way to plot data is to create a figure and then to create axes that go on that figure. So what we've done here is we have created this figure called fig and an axis called axs. And so what this does is this says, give me a figure with 2 rows and one column in order to add graphs on top of. And I want this top and bottom figure to share an x-axis. So if you see, what this does is this says, I don't want any data, I don't want any ticks on this top x-axis. Excuse me, I can't speak. And just put them on the bottom. So the share x is true. And then the figure size just says, I want this to be 20 by 10. So here we are grabbing, so we have the securities, which are the securities is going to be a pair. So for example, it'll be this USVP and STL. So I'm saying set this security as the first one, and then this color tab blue is going to allow me to change the color of the time series for this blue one. So AXS0. So what this is doing is this is indexing into this top axis. And so I'm saying I want this top axis to plot all of the prices that I enter for this security. And we're going to set those to be color blue. And so then you can also access the Y label of this.
Sorry, I think this stuff can be like this isn't really technical, so I'm just thinking
Right.
like people can just learn this on their own time. So
Yeah.
like I don't want to like I don't want to like waste your time teaching you this stuff when like people can, like this. I think this stuff can be like pretty easily self-learned, but like the other concepts are.
Sure.
So let's just get this for now. I'm sorry.
Yeah. I mean, yeah, not a problem. I mean, I can. But yeah, so basically, this first plot is taking care of this top axis, and then this right here is so that we can set this top axis to have a different scale on the right side. And then this portion right here is plotting the spread of the securities. So we just plot the spread, and then we set the X and Y label, set the title, and then add these horizontal lines for the mean, and then the one standard deviation. And then this plot explain variance. That's plotting these scatter plots. So we're just plotting the first and second, it's plotting this right here. So we're just summing the percent of explained variance of each of the principal components, plotting it on a 2D right here, and then just setting the title and everything. And then plotting loadings is just plotting this right here. So it just loops through each of the loadings for each of the securities, and then plots them on the axis. And then this plot clusters is how I got these right here for the 2-dimension and the 3-dimension case. And then here is, this was the helper function for the Hurst that we calculated earlier, of the norm spreads. So here's a Wikipedia page explaining some of the Hurst exponents and where I got the formula for the Hurst exponent. So right, yeah. So this is just this is where I got the formula for the Hurst exponent in order to calculate to find the Hurst exponent of each of the securities. And then again, it says where a value of 0.5 indicates a completely uncorrelated series, less than 5 indicates one where the price series reverts back to the mean. And then you use this polynomial fit function in order to find the Hurst exponent. For the half-life, you can find the formulas for half-life over here, but it's the time required to reduce to half its initial value. It's common in a lot of different fields outside of finance as well, but this is where you can find the formulas that I just turned into Python code for the half-life function. So you can just find those there. And then this count crosses. So this is just counting the number of times that each of these black lines crosses over this 0 number right here. So each of these statements will either return a true or a false. And so I'm saying, look at this period and then look at the next period. And if this current period is above the mean and the next period is below the mean, give me a true. Or if the current period is below the mean and the next period is above the mean, give me a true. Or if the current mean equals 0. And so what this does is this just gives you a list of true and false of whether these black series cross over the mean. And then just this sum function in Python, when you have just a list of true and falses, the sum will just give you the number of trues. And so this is just an easy way to vectorize looking at whether or not the series has crossed the mean. And then this is just a z-score that I used at one point in this class. So yeah, I mean, I think that really summarizes a lot of the underneath the hood of this class. I mean, I'm happy to go over this later or in more detail if people have any questions about it. And I mean, there's some stuff that certainly can be improved upon, I'm sure. If you guys have any suggestions, I'm all ears. But yeah, thank you for the time.
Yeah. Oh, thanks for. Okay, that was like freaking. That's pretty cool. And this is pretty big project. Like most of my stuff is like a third or fourth. Yeah. So I'm gonna stick around just if anyone has any questions, and I don't know, or anything. It doesn't even have to be about this, but thanks to everyone who came today. I'm gonna record everything. I mean, I'm gonna save the recording and upload it to YouTube. It's gonna be on our ATC channel, and so I'll just okay. So let's see. Do you guys have any last minute questions?
Yeah, sure. I mean, I think that was cool. Also, I think you answered this, but how did you find this paper again?
I found this paper on Hudson and Thames. They're a research group. They're a research group out of London. They have this. Let me drop.
Yeah, I think because I was looking at Hudson and Thames just now, and like I think I saw the paper about like optimal entry and exit, but not like this one specifically.
Right. So I found out about Hudson and Thames through. I dropped it in the chat right here. So they have this Python package, ML FinLab, where they basically go through and just implement a bunch of papers from machine learning applications in finance. And so I encourage you guys to look through this online documentation. They have just tons of algorithms that you can just plug and play with, basically. Excuse me. And then they recently had a skill set challenge for and this was the paper that was linked within that challenge. So what I just reviewed was actually my application for that project.
Oh, I see.
Wait, hold it. Oh, that's pretty cool. Like, wait, do you get anything if you win?
No, I think no. This is just my application for the apprenticeship. So.
Oh, the apprenticeship. Oh, so you
Right.
become
Yeah.
a friend.
Yes. Yeah. So it's like essentially like an internship.
You get paid?
No, I think no. No. This is not a paid one.
Oh, that's
Oh,
Yeah.
that's great.
unfortunate.
But still pretty cool.
But yeah. So that's how I found out about this one, or about that paper. But yeah, I encourage you guys to look through that Python repository that I dropped in the chat. I mean, they've got just a ton of machine learning applications that are free to use, and so you can just use them whenever you want.
It's pretty cool.
Oh, it's annoying. Some of it's Patreon locked or something.
Yeah, I saw that too. It's kind of hilarious.
Yeah. So you can you can just download you can't see the documentation for some of the things, but you can just download the code and then just look through the source code. I mean, it's.
Oh, I see.
Yeah.
They're non-profit, but then they freaking lock everything behind.
Yeah, I mean, in finance,
bro.
you typically want to be secretive, right? There's no point for people to just say like, we found this profitable thing. Let's just share it with everyone.
No, they're a non-profit though. They're a non-profit.
Yeah. But
like-
typically in finance.
Oh yeah, good point. So
Yes. I only heard about this because you were at the 2 Sigma thing and you said there was.
Oh really? Oh yeah, I think I
Yeah,
saw your name. Well, that's actually kind of crazy. Yeah, nice. I freaking advertised.
Yeah.
At the 2 Sigma meet and greet. Okay. Yeah. Thanks for coming. Okay. That's about it.
All right. Hey, thanks everyone.
Oh yeah. That was awesome. Okay. I'm gonna end the meeting now. So.
Yeah.
Bye,
Yes.
everyone.
See ya.